So at the beginning of this course, we saw that we had a line element that was written like this, the invariance of the interval, and we said that this is okay if space-time is the same everywhere, and that ultimately we would need a differential version of this, so a minus dt squared plus dx squared if we're doing, x and t. It's a two-dimensional space-time. And we just add the y and the z as well here. And we just discussed how gravity can be transformed away locally, but not globally. And so it's this kind of object that we're going to need. And we've also seen that we can write this ds squared as this metric tensor, which is, we're summing over these indices, A and B, and this gives us this kind of an object. And some of them are 0. We can combine these to give us this kind of an object. And of course we know that this is dt squared plus dx squared, as we just wrote. And so this is these are the components of this metric tensor, right? With this is eta 0, 0, this is eta 1, 1, this is eta 1, 0, and 0, 1, the diagonal terms. And to sort of focus a little bit on the mathematical properties of this kind of object, let's think about space and the infinitesimal distance in space, and then we'll come back to space-time. So, if we're in xy coordinates, then our infinitesimal distance, and we're in the xy plane, say, would be dx squared plus a dy squared kind of object, right? And the metric tensor here has components slightly different from this, because they're just 1 and 1 as opposed to minus 1 and 1 here and here. So here would be 1 and 1 and 0 and 0. And now we can imagine changing coordinates. So let's imagine changing from xy coordinates to our theta coordinates, where r is, of course, just the square root of x squared plus y squared. And theta is the inverse tangent of y over x, where r is equal to r, x equals r cosine theta, y equals r sine of theta. And if we make a little drawing of this x and y, we are considering some point, and so this is an angle theta. Say this is r. This here is r d theta. Right, this is d theta, and this is a little dr, and this is a little ds. then ds squared is equal to dr squared and r d theta squared. So it's dr squared plus r squared d theta squared, which we can write as, in terms of this metric tensor, now I'm using a different symbol, GAB, just because the components will look different. This is a more general term, but it's the same kind of object that we were talking about here. And these are general coordinates. So this thing has to reduce to dr, well, I just wrote it here, so I'm not going to write it again. Oops, not the best eraser. But the point is that the tensor that does the job of giving us this distance in these different coordinates looks like this. Okay, so it's not 1, 0, 0, 1. It looks like that. And so let's sort of summarize the ideas here. So we can describe the metric properties of the space or of space-time in any coordinates we want. There's nothing deep about that. And this, so far we've been looking at a space that's flat, right? So the 1, 0, 0, 1 for the metric in x, y coordinates, as well as the 1, 0, 0 r squared for r theta coordinates. Both of these metrics describe a flat space. And for space-time, we saw that the flat space was, a flat space-time rather, was described by a metric with these components. But the point is here that in this flat space, whether we describe it this way or that way or in some other way, we can always find a coordinate transformation that takes us from coordinates where the metric has components that look like this to a metric that has components that look like this. And the same thing will be true in space-time. So we generalize the ideas of space to space-time, and so we can imagine evaluating the metric for flat space-time and thinking of transforming that. It's always possible to transform to a metric that has these components for t and x, as opposed to some other t bar, x bar. And of course, if we include, if we do 3 plus 1, t, x, y, z, and we can do this in some other coordinates, then we can always transform. The idea is, the parallel is that we can always transform to this form. And this will always be true even when we are in general relativity and space-time is not flat, but only locally. So this is the mathematical equivalent statement. Physically, we can transform away a gravitational field locally, and mathematically that amounts to saying that locally we can have a metric that has this kind of character.